left 4, we said this is delta x times f of x1 plus delta x f of x2 plus delta x f of x3 plus dot dot dot, right? So this is the constant that goes outside. So that's why we can write delta x times the sum of f of xi from I equals 1 through n. Because all those have the same width. So the base of, or the width of the rectangle, same one. So when we divided the interval between 0 and 2 by 4, we got 0.5. So that was the 0.5 that was in front of each product, or was part of each product. So that's why we took it out. So that's the reason why the sum of delta x times f of xi is the same with delta x times the sum of xi. Because this is a constant, it does not depend on where we are in the interval. If we are in the first subinterval, or the middle of the subinterval, or the last subinterval, delta x doesn't change. All rectangles have the same width. And being a constant does not depend on where we are. So it comes out. Is this better? Okay. Next question. Anything? Is there anything that you would like? Greg, you had something? You wanted to work on something? I forgot what it was.
It's going back to chapter 4.
That's fine. That's why you should, because we're getting ready for the test, right?
Yeah.
Yes. F of x?
It is f of x equals 7 sine x plus cotangent x on the interval pi to pi. And we had to find...
You mean negative pi to pi?
Oh, negative pi to pi, yeah.
Okay.
And we had to find the interval of increasing and decreasing the inflection points in the concavity up and down.
Okay, perfect. They are all connected. Very good. So, we're not asked to graph. We're not asked to find the x-intercept, y-intercept. We are only asked to find the first derivative and what it entails, and what it teaches us or tells us about the function, and the second derivative.
Okay.
Yes?
Yep.
Okay.
Yeah, that's it.
Very good. So let's find f prime, which is 7 cosine. So this is sine and cotangent?
Yes.
Okay. So then minus cosecant squared x. Cotangent prime is negative cosecant squared. So we're trying now to find or solve this trigonometric equation. 7 cosine x minus cosecant, which is 1 over sine squared x equals 0. It's not a friendly situation. We'll have to multiply both sides by, or find the least common denominator. So this is 7 cosine x times sine squared x minus 1. And now we know that a fraction is 0, and we know that a fraction, when a fraction is 0, only the numerator can be 0, correct? So from here, we have to write that 7 cosine x, I have to change this into 1 minus cosine squared. I can't solve a trig equation that is not already in the factored form with more than one trig function in it. So now we distribute, and I get in trouble. Why I get in trouble? Because I have 7 cosine cubed. So in order to determine or solve this equation, I have to use a calculator. Or Newton's method. Whichever you prefer. So when I distribute, I have 7 cosine x minus 7 cosine cubed x minus 1 equals 0. Are you sure that this is the function? It's very possible. I'm not disputing anything.
Yeah.
So I'll multiply both sides by negative 1. So 7 cosine cubed minus 7 cosine x plus 1 equals 0. I don't know how to solve this. I either use Newton's method or I use the calculator. I'm assuming between negative 5 and pi, I may have 3 solutions. I may have one solution, I have no idea. It's cubic in cosine. So I have to solve this equation first. Like 7y cubed minus 7y plus 1 equals 0. And I don't have a tool for this other than Newton's method. So I can create a function and determine these solutions. But I don't have a way. So let's put in the graphing calculator. I'm not avoiding Newton's method. It's a very good practice for this test anyway. But I just want to see, because a cubic function can cross the x-axis once or 3 times. It cannot cross twice, because it does this, either once or 3 times. So either it goes an increasing or decreasing, or it does this and crosses 3 times. It's cubic. So it cannot have more than 3. It cannot have less than 1, at least 1 or 3. So in y equals, I'm just curious now. See what you're doing to me? So 7x cubed minus 7x and plus 1. Okay, so
Would you put it all in the negative though?
it doesn't matter. I just want to solve the equation. Yeah, you're right. So I know what you're saying. But for now, I'm not really looking at the function. I just want to see how many solutions will this have. It can only have 1 or 3. If it has 1, then the other 2 are imaginary. If there are 3, then 3 real solutions. But yes, of course, I'm not graphing anything. I'm just trying to find the solutions of this. Either 1 or 3 reals. And I don't know what I changed here, but it doesn't show me the graph anymore. So I'm going to use a standard viewing window for now. Let's see what happens. I may not see anything. Who knows? So here they are. 3 solutions as expected. I don't know what they are. Potentially -1, potentially a little bit on the positive side, and potentially 1. I don't know. So I can determine them. And after I determine them, then I can solve the equations. Cosine equals this, and cosine equals that. Okay, so I believe this is going to be -1 and this is 1, but this one I have no clue. So it doesn't matter. So I go to second in calc and I want zeros. And the first 0 I'm going to say is between -2 and 0. Between -2 and 0. And I think it's going to give us -1, but who knows? It's not exactly -1. So it's -1.06. However, I have to disregard it. I'll go back to the other ones. So the first y was -1.06. But -1.06 can never equal cosine x. How come? Exactly. It's outside of the range of cosine. Cosine has to have an answer between -1 and 1. If cosine is greater than 1 or less than -1, there is no x. So this one has no solutions. Okay, now let's go and try the other one. So again, second in calc, I want the 0. This time I see it's between 0 and 1. I think I didn't take it, sorry. 0 and 1. Maybe it did. Okay. Oh, so that's before 1. Okay. Okay, so then, second calc again, I want the 0. So I'm going to say between 0 and 0.5. Okay, now give me what I'm looking for. Okay, so this is okay. So cosine x to be 0.145967, it's okay. Now finally, let's determine the other one. So that one is between 0.5. Do we understand what I'm doing? Is this okay? Yes? Okay, so the 0 this time between 0.5 and 1. No guess. Okay, 0.91. So 2 are possibilities. Cosine x equals 0.918993. How did they come up with this problem? Okay, so now I have cosine, 2 possibilities. But between negative pi and pi, I can have two angles for this and two angles for that. So 4 x values. And then we have to study the sign.
We don't have to do this problem.
But you have to do it, so. Okay, so let's determine from here, let's determine x, and from here, let's determine x. Okay, back to the calculator. So, cosine inverse of 0.145967. Okay, and the other one, cosine inverse of 0.9189943. 819, yeah, 9, yes. Okay. Okay. Wait a second. Okay, I was in degrees. Okay, that's fine. Okay, so we have, I'm going to just put approximately 82 degrees and approximately 23 degrees. But here's what happens. Cosine is positive in this quadrant and this quadrant, right? So let's see, 82 degrees is this angle, but also this angle. So 82 degrees or 360 minus 82 degrees both have the same cosine. So between negative pi and pi, we have two solutions, basically. One angle is 82, and the other one is negative 82, because the domain was given between negative pi over 2 and pi over 2. So this angle, negative pi over 2, has the same cosine, and this angle has the same cosine, 0.14. This is 0.14, not on my graph, I know. So this is 0.14, because cosine is, and the angle is 82. And this is also 0.14 for cosine of negative 82. So when I start my table, let's start on the same next page. So that was x, negative pi to pi. So this is, it was denoted by f, yes. So f prime of x and f double prime. I'm just curious how they came up with those answers. Not that they can't, but what they presented and how they are doing it. I'm just curious now. I cannot put negative 82 degrees in here and positive 82 degrees because everything is in radians. So I have to change it into radians in a minute. So let's come back and finish up with 23 degrees, and then we'll change all four. So 23 degrees is this angle. This is 23. But also, another angle with the same cosine is this, which is negative 23 degrees. So back to the table, I have to write negative 23 degrees and 23 degrees. So I have 4 entries to make, but they have to be in radians. So I have to change them into radians. So once I put on these numbers, okay, so remember the conversion. Pi radians is 180. So if I want 1 degree in radians, is pi over 180. So I have to multiply 23 by pi pi over 180 and 82 by pi over 180 to change those into radians. So what do we get? So 82 times pi divided by 180. I got 1.43. Negative 1.43, positive 1.43, and then the same thing with 23. And I got negative 0.4 and positive 0.4. Okay, now I have to determine the sign. So I have to pick an angle here, here, one here, one here, one there, to determine the sign of the first derivative. So let's put in the first, at least let's finish the first derivative, and then you got the picture.
Yes.
And I'll help you with the second derivative. After class or next time.
Okay.
Okay, so where is my first derivative? Now I have to put the correct derivative in there. So 7 cosine x. I have to make sure that, because now I have to put in radians. So make sure that you have the mode in radians. Okay. So the derivative was 7 cosine x, right? Minus cosecant squared. And that is minus 1 divided by, in parentheses, sine x, close the parenthesis, close another one, squared. Because I don't have a way of writing cosecant. There's no key for that. Okay, so now I have that, and from the table, I would plug in negative pi. Okay, second and table. Negative pi. Negative. Did anything happen? Did I do anything here?
I got an error too.
That's okay. So then we would have to be, but this should stop. It's not stopping it. I have to let it run now. I didn't mean to graph it. I don't care for the graph, because we're only talking about negative pi to pi. Anyway, so second and table, fine. So I cannot plug in negative pi. That's okay. But I'm going to plug in negative pi over 2 then.
Bless you, bless you.
Bless you.
It was negative. Did I copy something incorrectly? So 7 cosine x minus cosecant squared, and that's,
It didn't let you change the X.
Yeah, that's
they
what
needed
it
to
was.
change
It's
the
not letting
setting.
Do you have it where you can type in that?
no, I have it correctly. Oh, how come did that, when did that change? Sorry. Okay. Okay. So let's check. With negative pi, it didn't work. It gave us an error. Very good. So then negative pi divided by 2. Good. Negative. So now I want to plug in negative 1. Positive. And now I want to plug in 0. Yes, because of the cosecant. So I'm going to plug in 0.5. Okay. And 0.2. Okay. And then 1. And then pi over 2. That's not the one. This is the one. Divided by 2. Okay. So now, here's what I copied. So to the left of negative 1.43, we had negative. Between negative 1.43 and negative 0.4, we had positive. Between negative 0.4 and 0.4, we had negative. Between 0.4 at 1, it was positive. And then outside was negative. Well, this is insane, right? Okay, now we have, in case they're asking for points, then you have to plug in the function this,
Okay.
and this, and this, and this. But now I know the increasing, decreasing. I know it's decreasing between negative pi and this, union this and this, union 1.43 and pi, because the derivative is negative.
Yes.
And it's increasing between this and this, union this and this, because the derivative is positive.
Yes.
And then I have to find the second derivative. And who knows what I come up with?
Right.
I have no idea. So it's going to be another messy situation. Now this becomes -7 sine, and this is -2 cosecant times the cosecant prime, which is cosecant cotangent.
Okay.
I mean, if we have time, we can do this
Yes.
after class.
Yeah, let's do that class.
But I hope that you copied it incorrectly. That's my hope.
Yes.
Maybe you didn't.
Oh,
Yeah.
you mean the problem? No.
Yes, I
No,
hope you copied.
No.
Yes, Eddie.
With any graph of in trigonometry, it's always going to be oscillating. Like,
That is true, but I don't know where. And the problem was asking to find the intervals of increasing, decreasing. And if I don't determine these, I will not be able to tell.
Okay.
Now, how many decimal digits do they want on this? Because you may put in -1.43 and they want -1.432 or 1.435.
I don't even want to think
Did
about
they say?
that. No, I would have written it down, but I don't think they said anything specific.
So that's why I still hope that you copied it incorrectly. And it's a little bit easier than that. Okay, but it was a good experience.
Yeah.
So now you have to find the second derivative, so that equal to 0 is going to be a mess, and we can look at the trig equation.
Sounds great. Okay.
Sorry about that.
No, you're fine. I
Okay.
didn't realize it was that hectic of a process.
Yes, because of solving cubic equation in cosine.
Okay.
So we expected either 1 or 3, and we had 3, but one of them was out of range.
Sure. Okay.
Then we would have gotten 6 solutions. So now we're happy that that one was out of range.
Gotcha.
Okay. Any questions for me? Here's my next question for you. Would you like us to practice another limit of the Riemann sum? That's where we left off last time. We only had 1 or 2. Would we like to work again on the limit of a Riemann sum to find the exact area? Perfect. So please choose a linear function, a quadratic or cubic function. So we can go through all the steps again. Any function you want, linear, cubic, quadratic, and an interval. Now be very careful. If you decide, let's say, for the interval not to start at 0, it's going to take us a while, and I'll show you why, but maybe you want to see one example when the interval doesn't start at 0. The easiest thing is to have an interval from 0 to 5, 0 to 2, 0 to 3, 0 to 10, whatever you want, but start at 0. But we don't have to. Now, if you choose a cubic function and do not choose 0 as the starting point, it's going to be messy. Only because we have to cube a binomial. Okay, so please choose a function, any function you want, and let's start.
X squared minus 4.
Okay, x squared minus 4. Also remember, the answer could be negative. Is it possible for an area to be negative? Yes. The positive area is above the x-axis, the negative area is below the x-axis. And I do like some of the graphs in the book. I mean, overall, I do like this book, to tell the truth. So if we're asked to determine the area between 0 and 3, as you notice, this piece is much bigger under the x-axis than this piece above the x-axis. So obviously the answer for this would be negative. Okay? So do not get surprised. The answer could be positive, could be negative. Okay, let's choose an interval. So I would spice it up a little bit, at least with an x here. And spice it up. So now we can, on such a function, we can start at other points than other x values and 0. It's not a big deal. But if you choose a cubic function and you have here 1, 4, then we have to cube a binomial, which is not difficult, but it will take a while. Okay, so please let's use an interval. We need an interval, otherwise we can't determine the area without an interval.
2 to 6.
2 to 6 it is. Excellent. Remember, we need 3 preps. Mandatory before you put everything together in the limit of the Riemann sum. And the first prep must be delta x. So what does delta x equal to? By definition, is b minus a divided by n. b minus a divided by n, which is 4 over n. In step 2, we have to find f of x, we have to find xi. So what did we accomplish so far? We determined the width of each subinterval. How many are they? N. And n will go to infinity. Now we have to determine the generic xi. Do I need to explain? Please tell me if I need to explain what xi means. Yes? Okay, so let's look again. So this is the interval. Is delta x clear? So we have the interval between 2 and 6, and we're dividing it into n subintervals, and we just determined the width of each. How much is the width of each? So there are n subintervals. What is the width of each and every one of them? 4 over n. This is the width of each subinterval. 4 over n, 4 over n, 4 over n, 4 over n. Is that clear? Okay, so now we want to determine a generic x. And we started with this first one, and we said that x sub 1 is 2 plus 4 over n. Would you agree? What about x sub 2? What will that equal? 2 plus how many delta x? So it would be 2 plus, yes, but let's write it for everyone to see. 2 delta x, correct? What about here? Let's say I got to xi, the ith interval. I goes from the first subinterval to the last subinterval, right? So I is between 1 and n. So I got to this subinterval now. This is delta x. So I would like to determine xi. What will you write for xi? Xi, this point, is 2 plus how many delta x's? If for x2 I needed 2 delta x's, if for x1 I needed 1 delta x, how many delta x's do I need to get here? From 2 plus how many? I delta x. Do we see that? So this will be 2 plus I delta x. Without identifying xi, I will not know what to plug in the function. Do we agree with xi being 2 plus I delta x, which is 4 over n? So now we determined xi to be 2 plus I times delta x, 4I over n. You understand we have to create a generic or general formula that goes from 1 to n. Is this better? Is xi better? Yes? Okay, now, third prep. I'm going to copy the function on this page. You don't have to copy it again. So we have f of x equals x squared minus 4x. I need to find f of xi, which means this, f of 2 plus 4I over n. Why do I need this piece? Because I have to put it in the limit of the Riemann sum. So I have to plug in this binomial in here and square it, and again here and distribute, making 4. So let's write it for everyone to see. So this is 2 plus 4i over n, everything squared, minus 4, 2 plus 4i over n. When we square binomial, we know for sure we get, thank you, a trinomial, thank you. So the first term squared is 4 plus 2 times 2 times 4, 16i over n, plus the second term squared, 16i squared over n squared, minus 8 minus 16i over n. There is no reason why I would not simplify this fully before I put it in the limit of the Riemann sum. The limit of the Riemann sum is a lot of writing anyway, so I'd rather simplify it out here fully before I put all the pieces together in the limit of the Riemann sum. So in descending order, I have 16i squared over n squared. Ah, very nice. And then minus 4. That must have been my touch to know as constant. Wonderful.
That's a spice.
Yes, I was trying to spice it up. Okay, finally, after all these 3 preps, we're ready to put everything in the limit of the Riemann sum. So let's write the area equals the limit. Let's write the formula first. From I equals 1 through n, from delta x, f of xi. Now you understand why we started with this, then we determined this, and then we determined this. Is that clear? In order to be able to put everything together now, I needed this piece, I needed this piece in order to determine this piece. That's why those 3 preps. Okay, so now we can put everything together. So we have limit as n approaches infinity from the sum from I equals 1 through n, the sum of areas. Delta x was 4, right? It was 4 over n. And here is multiplied by this, which is 16i squared over n squared minus 4. As we discussed a minute ago, maybe 20, this is a constant, it goes in front. It does not depend on I. It's that delta x that can be pulled out from each product, delta x. So then I will write the limit again. Do not drop the limit, please, the limit operator. 4 over n. Now, let's use the property that says the sum of the 2 terms is the sum of the first. I'm not distributing, looks like it, but it's not the distributive law, it's the property. The sum of the first term minus the sum of the second term, to cut back on writing a little bit. So I would have the sum from I equals 1 through n, from 16i squared over n squared minus the sum of 4 from I equals 1 through n. Now I will apply the same property, taking the constant in front again from each. What is the constant? Can anyone give us the constant here for this sum? 16 over? Correct. This is the constant that goes in front. This is the only piece that depends on I. Here, it's 4 times 1. So I'm going to put 4 in front, the summation of 1. Because that's what we have. We don't have summation of 4. But we are using the property that allows us to put 4 in front. Okay, so this is limit. N approaches infinity 4 over n. And this is 16 over n squared, the sum of I squared, minus 4, the sum of 1. Now, this will disappear, and this will disappear, because we have the formulas or the identities. So this will be replaced, and this will be replaced. What do we replace them by? Yes, this one is the easiest one, right? The first one, which is n. And this is the ugliest one, right? It's the n plus 1 to n plus 1 over 6. So this is n plus 1 to n plus 1 over 6, and this is the n. So that is the drawback, if you want, when we look at a quadratic function versus a cubic one. So with a cubic, we would have had difficulties, not difficulties, but it would have taken us some time to raise a binomial to the third power. But now here, I have, we give up something, we win something. So now I have to work with that, but that's okay. So now the summation notations are gone. Limit as n approaches infinity from 4 over n, 16 over n squared times n plus 1, 2n plus 1 divided by 6 minus 4n. I could simplify by 2 and by n. One n will go away and 1, 2 will go away, but it's still the least common denominator will still be 3n. So this will go away and this will go away. So this is limit n approaches infinity 4 over n. The least common denominator is 3n, and this one needs a 3n. So I have to distribute 8 to this product, but I'm going to multiply first. And I get 2n squared plus 3n plus 1 multiplied by 8. So it's 8, 2n squared plus 3n plus 1, and minus 12n squared. Are you with me? Is this okay? Yes? Great.
How did we get 3n again?
I simplified 16 and 3 by 2, and I simplified an n, so then the denominator now is 3n,
Oh.
and it has to stay.
Got it.
And this is over 1, so it gets a 3n.
Okay.
Better?
Yep.
Everyone, questions? Is this okay? Okay, so then now I multiply the denominators here. So the denominator will be 3n squared. And let's see what we get. 4 is outside, so 16 minus 12, 4n squared, plus 24n and plus 8. Finally, limit as n approaches infinity, 16n squared plus 96n plus 32 divided by 3n squared, and we know the answer already. If you say, no, I don't remember that, show me with L'Hopital's rule, then I'll show you with L'Hopital's rule, because it's infinity over infinity. So it's 16 over, do we agree with 16 over 3, or should we work it out with L'Hopital's rule? Huh? With L'Hopital's rule, or you remember this? It's okay if you don't.
I think like that.
Yeah, so it's the same degree over same degree, and n approaches infinity. Is everyone okay with that? Or should I apply L'Hopital's rule? Andre, should I apply L'Hopital's rule? You want me to apply L'Hopital's rule? Yes, okay, let's do that. So is it clear that this is infinity over infinity, right? We agree with that? So then this becomes limit n approaches infinity from 32n plus 96 over 6n. Agreed? Is that okay? So 32n plus 96, this is 0, and then 6n. Is that okay? And then this is infinity over infinity. We apply limit, the L'Hopital's rule again. So this will become 32 over 6, which is 32 over 6. that changes into 16/3, as we knew from the beginning, only because they are the same degree. Otherwise, the answer is not 16/3. Better? Good. Yes, no?
Now if that 3n was to the third, it would be 0. Right?
Sure, it's not going to happen though.
Right.
Yes, absolutely. That is not going to happen. Why? Because these functions are all polynomial. So we're not going to have any difficulties with them. Good. So do we understand now the procedure for the limit of the Riemann sum in the exact area? Do you think we need another example? Or for now we are okay? Yes? Yes. Go ahead. Yes?
I understand what you did, but
Yes.
could you explain the
Yes?
sigma summation notation?
Yes. You mean the properties or what it means or
Yeah, like what it means.
what it means? Okay. So it came about when we wrote something like 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. Well, we don't really like this notation. It's too long. It's a lot of writing. So we can condense this notation using this symbol, which is the Greek letter S, saying, okay, so this is the first term, so I is 1. This is the second term, so I is 2. This is the third term, so I is 3. Dot, dot, dot. For this, I is n. So from I equals 1 through n, from what? Well, from I squared. When I is 1, I get this term. When I is 2, I get this term. When I is 3, I get this term. And how come that it's the sum? Because that's what this signifies. I have to add sequentially each term after the other. So we prefer this notation than listing everything like that.
Would it matter if you like change the I or like the index?
Yes, sure. So I can have, for example, from k equals 2 to 5, from 5k plus 1. What does this mean? When k is 2, 5 times 2 plus 1, plus when k is 3, 5 times 3 plus 1, plus when k is 4, 5 times 4 plus 1, plus the last one, 5 times 5 plus 1. That's all it means. But instead of listing all those 4 terms, I'm saying from k equals 2 to 5, from 5k plus 1.
I got it.
It's a condensed way of writing. So now imagine if I want to add all the areas of all rectangles, then I have to say from the first one, delta x times f of x1, plus delta x times f of x2, plus delta x times f of x3. But instead I write, better? Yeah. There is also another one, which we will not use, not in this class. This one. What do you think this one means? It's a product. So we can have the product of different quantities. So we can have, I didn't write what, so the pi from I equals 1 through n from, let's say, 2i plus 1, which will mean 2 times 1 plus 1 times 2 times 2 plus 1 times, but not sum, because this is a product now, times 2 times 3 plus 1 times dot dot dot, the last one, 2 times n plus 1. So there's another condensed form, but this time this is 2 times 1 plus 1, 2 times 2 plus 1 times dot dot dot, only 3 dots, they cannot be more. That's by convention, 2 times n plus 1. So then these are n terms. But pretty much the same idea, but it's a different operation there, though. Okay, are we okay now with the summation notation with the limit of the Riemann sum? Yes? Okay. Okay, we're ready to move on. We know that in area, I'm going to write it one more time. However, it can be determined, so this is the exact area. The exact area under the graph of function f of x between such and such, a comma b. There is another way of determining this area. This time we're going to use the Latin s, but stretched. So this is the exact area on the interval a comma b under the graph of f of x. Okay, so this stretched s from a to b, I'll tell you what it is in a moment. What do you think of what? So this has to have a correspondence in here, and this has to have a correspondence in here. It's the same thing. It's just that these two disappear and are replaced by this symbol. But what we calculate this from has to be the same. It's still f of x, it's still height times width, or width times height, plus width times height, plus width times height. It's the same thing. And it's still a sum. So this is still a sum. Still a summation of the areas. So what will I put for this? What will this be replaced by? Of course. And what will this be replaced by? Very good. Indeed, f of x dx. And this is the definite integral between a and b. The definite integral is always a number. So how do we read this? The integral from a to b, I meant lowercase b, sorry. From a to b, from f of x dx. From f of x times dx. And this is the exact area under the graph of f of x between a and b. The same thing. These are two different ways, sort of, I would say different, right? Two different ways of determining the area. This is the definite integral, which is always a number, and that is the limit of the Riemann sum. Now, one comment here, extremely important. F of x must be continuous on the interval a comma b. Otherwise, we cannot determine this the integral using the theorem that I'm going to present in a minute. So then several of my students always ask me, okay, but how are you going to determine the integral if the function is not continuous? You have to wait till Calc 2 for that. They are improper integrals. And you will be able to determine the integral only if it converges. If it doesn't converge, there is no number. So one other thing that I was going to mention here, the integral from a to b from f of x dx is a number. Because we have another type of integral, which will not be a number. We have two different types of integrals, and this is the definite one that gives us the area, and the result will always be a number. The function must be continuous. Okay, so now I would like us to look at the fundamental theorem of calculus. It has two parts. We're going to look specifically tonight at one of them, and then later on we'll talk about the other. In some books, what I'm going to show you now is part 2. In other books, it's part 1. It doesn't matter. I'm not going to ask you. We have to decide what we want to use as part 1 and part 2, but you know what I mean. Okay. So the part that I'm referring to right now shows us, it shows how to calculate a definite integral. This in this book is called part 2. So the fundamental theorem of calculus shows us how to calculate the definite integral. Part 1 is a little bit more sophisticated, we will get to it. So, okay, how does it do it? The integral from a to b from f of x dx equals, and now we go back to our notation from last time. Can you please tell me how you will denote the antiderivative of f of x? I need the notation. Yes, Sam? Very good. So it will be uppercase f of x, a vertical bar from a to b, which really signifies the difference when we evaluate f at b and when we evaluate f at a. This is the fundamental theorem of calculus, part 2. It shows us how to evaluate definite integrals for continuous functions, of course, for continuous functions. Okay, now I would like us to go back to our invention. What was it? We had f of x equals, what was it, 2x squared or just x?
X squared minus 4x.
X squared minus 4x? That's what we had? Okay, very good. What was the interval that we came up with?
2 to 6.
Very good. So now we want to determine the area. Please dictate. I want to find the area now using or calculating the definite integral. So this would be the integral from 2 to 6 from, in parentheses, dx. Very good. There is no integral without dx. Can anyone give us the antiderivative of x squared? What function prime is x squared?
X cubed.
Very good. Minus 4. What function prime is x?
Wait, no, it's not minus 4. Yeah. It would be 2x.
So x squared over 2. Good. From 2 to 6. So one more time. Let's check. X cubed over 3 prime is x squared. Would you agree? Negative 4x squared over 2 prime will be negative 4x. Agreed? Yes? Good. So the fundamental theorem of calculus says, now this is your antiderivative for this function. Plug in 6 and subtract when we plug in 2. Okay, I'm going to plug in 6. So this is 6 to the third minus 3. I'm going to simplify here, and I'm going to write minus 2 times 36. And then minus, when I plug in 2, I get 8 thirds, and 4 times 2 is 8. So I plugged in 6 in the antiderivative, 6 cubed over 3 minus 2 times 36, and minus when I plug in 2, the lower limit, 8 thirds minus 8. Okay. So 6 cubed divided by 3 is
72.
how much?
72.
And you divided by 3 already?
Yeah.
Very good. So you said 72. Minus 72, I like that very much. Minus 8 thirds. And minus 24. So this is 21 over 3. Negative 16 over 3 with minus in front, 16 thirds. Bottom line is, do you prefer this method or the limit of the Riemann sum? First of all, the other one is completely limited to 3 functions. This one, it doesn't matter what function we use, as long as we can find the antiderivative. It doesn't necessarily mean that we can. If we're lucky and we determine the antiderivative, because on many functions we will not be able to. Yes?
How did we get the 24?
I have to find the least common denominator, because this is 8 over 1. So I have to multiply this by 4. Or by 3 to get 24.
Oh, okay.
And then negative 24 minus 8 minus 24 is negative 16 with minus in front.
Gotcha.
Better? Very good. Okay. Now I would like for a while to practice this. And let's choose some problems.